what does it really mean for an AI to think? Today, we're diving deep into cloud computing, the new infrastructure imperative. Data gravity, AI, and real-time applications demand elastic compute, global distribution, and zero-friction provisioning. On-premise systems are static, CapEx-heavy, and slow. Cloud native is now the baseline. Infrastructure is programmable, API-driven, consumed as a service. The market exceeds $600 B, doubling every 3 years. AI training requires tens of thousands of GPUs on demand. Only the cloud orchestrates at that scale. This shift reshapes every industry, serving as the foundation for AI and global scale applications. The shift is not a choice. It's an architectural necessity. But here's where it gets interesting: the static infrastructure trap. Traditional on-premise infrastructure provides fixed capacity, requiring months-long procurement. This static model cannot handle AI burst compute, global traffic spikes, or real-time data streams. Over-provisioning wastes capital. Under-provisioning causes outages. Deployment cycles of weeks kill iteration speed. Hardware-defined topologies limit redesign. Result: infrastructure bottleneck. Root cause: tight coupling of hardware and application prevents elastic scaling and API-driven automation. Modern workloads demand programmable, elastically scalable infrastructure the static data center cannot deliver. This model forces a trade-off between performance and cost. Both suffer. So what's the real problem? Let's talk about the root cause: hardware application coupling. Applications are designed for specific server configurations, storage arrays, and network topologies. Tight binding means scaling requires re-architecting the physical layer, reconfiguring load balancers, firewall rules, and storage LUNs. Provisioning is manual, error-prone, slow. Infrastructure's decisions are embedded in application code, preventing portability and elasticity. This coupling is the fundamental limiter of digital speed. The physical layer dictates application architecture. To break the bottleneck, decouple infrastructure from physical hardware, introducing virtualization and abstraction. This raises a critical question: breakthrough decoupling infrastructure from hardware. The virtualization stack decouples compute, storage, and network from physical constraints. Hypervisors create VMs. Software-defined networking abstracts connectivity. Software-defined storage pools disk resources. Containers encapsulate apps with OS-level isolation. Serverless eliminates server management entirely. Infrastructure becomes code provisioned via APIs. Cloud providers expose these abstractions as pay-per-use services. Result: elastic, portable, automated infrastructure deployable globally in minutes. The data center becomes a programmable resource. This abstraction transforms infrastructure into a utility provisioned on demand via self-service APIs. This is the genesis of cloud computing. Now let's zoom in on cloud architecture, a layered service model. IaaS, raw compute, storage, networking, virtualized, API-driven. PaaS, managed runtimes, databases, queues developers ship code, not infrastructure. SaaS, complete applications as a service. Serverless and container orchestration, Kubernetes, span layers. Each layer abstracts underlying complexity, accelerating development velocity. API gateways, identity, and observability are built in. This tiered abstraction balances control and productivity. The model supports any workload: legacy VM, cloud-native container, serverless function. The platform becomes an integrated ecosystem. Here's something most people overlook: cloud-native design principles. Elasticity, scale out automatically with demand. Resilience, design for failure. Circuit breakers, retries, multi-AZ. API first, every capability exposed via APIs. Automation, infrastructure as code, CI/CD. Observability, logs, metrics, traces as first-class citizens. Security, zero trust, encryption everywhere. Cloud-native applications are composed of loosely coupled, stateless services. They embrace disposability. Instances can be replaced instantly. These patterns exploit the elasticity and automation of the cloud substrate, non-negotiable for operating at cloud scale. Think about this for a second. The cloud-native component ecosystem. Compute, VMs, containers, Docker, serverless functions, Lambda. Storage object S3, block, EBS, EFS. Networking, VPC, load balancers, CDN, API gateways. Data, managed relational, RDS, NoSQL, DynamoDB, streaming, Kafka. Orchestration, Kubernetes, Service Mesh, Istio. Observability, CloudWatch, Prometheus, tracing. Security, IAM, encryption, network policies. Identity and access governance enforce least privilege. These building blocks are composable, API first, globally available. Each component is a managed service, eliminating undifferentiated heavy lifting. And this is where things get complex, from code to production. The cloud-native pipeline. Developer pushes code, CI/CD triggers build, test, security scan, artifact, container image, push to registry. Kubernetes orchestrates deployment with rolling updates and auto-scaling. Service Mesh routes traffic enables canary releases. GitOps, desired state stored in Git, automated reconciliation ensures reality matches declaration. Immutable infrastructure, no manual changes. Rebuild and redeploy. Observability captures logs, metrics, traces continuous feedback loop. This pipeline enables multiple deploys per day, zero downtime, instant rollback, defined entirely as code. But here's where it gets interesting. Impact, 10x velocity, global scale, 99.99% uptime. Deployment frequency, from quarterly to hundreds per day. Time to market, months to hours. Global reach, 30+ regions, one command. Resilience, multi-AZ, auto-healing, zero downtime, failover. Mean time to recovery under 1 hour. Change failure rate reduced by 80%. Cost pay-per-use cuts idle capacity, TCO reduced 40%. Developer productivity doubles. Innovation cycles compress. Cloud infrastructure velocity matches software velocity, unlocking continuous experimentation. This is the new operational baseline. So what's the real problem? Let's talk about next. Ambient cloud, edge, and AI native ops. Edge computing pushes workloads to data sources, achieving 10 as latency for real-time AI inference, IoT immersive experiences, AI native infrastructure. Cloud GPU clusters train models. Edge runs inference. Zero ops, self-healing, auto-scaling, AI-driven capacity planning. Multi-cloud, hybrid architectures orchestrated by single control plane. Convergence of 5G edge, cloud creates a seamless compute fabric. Cloud becomes ambient, invisible, pervasive, context-aware. Infrastructure operates autonomously. Developers focus on business logic. This is the operating system for the physical world. This raises a critical question, your cloud-native operating model. Build an internal platform that abstracts infrastructure complexity. Provide self-service APIs, golden paths, and policy guardrails. Empower development teams to deploy independently while ensuring security, compliance, and cost control. Treat infrastructure as a product, adopt product mindset, measure developer experience, iterate continuously. Golden paths reduce cognitive load and enforce best practices. Goal, frictionless developer experience, maximum business agility. This is the evolution from cloud adoption to platform-driven velocity. Adopt the architecture that made hyperscalers successful. Now, let's zoom in on the architecture of the next decade. Cloud computing is not a destination. It's the platform for continuous reinvention. The abstraction layers are now mature, enabling AI-driven, self-optimizing systems. The new frontier fusion of data, AI, and edge in an ambient compute fabric. Build on these primitives. The future is programmable infrastructure, invisible, limitless, responsive. Your architecture is your competitive advantage. This is the architecture of transformation.